Hi, Keith here. I've been asked to look at rarefaction, but I thought this would be a good opportunity to look at some of the other options that are available there on the diversity menu. Now before I do that, there's a couple of things I want to briefly mention. First of all, if you're doing things with diversity, then I'd strongly recommend having a look here at Estimate S. You can do a web search for it and you'll find it fairly quickly, or get the link out of the tab up there. It's quite comprehensive and well supported by documentation. The data set I'm going to use that you can see here is a set of species going across, and you can see there's quite a few, and a set of samples. Now I really needed a live or real data set here instead of working with my simulated data. This data source, I actually found it by going to this article about an R package used to analyze species richness, and this data set is, where was it? Okay, let's just go right down the end. It's this, the data has been sourced from this paper here, and it's looking at macroinvertebrates in soil, so that's what we're dealing with. Now, as far as past goes, the diversity options and calculations appear to be similar, if not identical, in past version 2 and version 3. So I'm going to use version 2, which is the one that most of the videos use. And before going to look at the diversity menu, it's useful to have a bit of a chat about diversity. Now the little diagram here is indicated to make a point about diversity, and that is that there are actually two different pieces of information, two different sorts of information we can get when looking at a community. Richness is the diversity of the community or assemblage in terms of the number of different species or number of different taxa that there are there, which in this case is 1, 2, 3, 4, 5. The other aspect of diversity that people are often interested in is evenness, and this community here is extremely uneven because 4 species are represented, as you can see, by one individual, and the other individuals are all of the same species. Contrast that to this situation where we have the same number of individuals of each of the species, and so visually it looks like a much more diverse assemblage or community, even though richness is identical. And trying to split out those two different aspects of diversity is one reason why we've got a plethora of diversity indices. Now what we're talking about here is actually alpha diversity, or diversity within an assemblage or community that's within the same kind of habitat. Whitaker, back in '60, actually defined two kinds of diversity: alpha diversity, which I've just illustrated, and beta diversity, which was related, as you can see here, to the change which occurred as you went from community to community or across different habitat types. And there's a Wikipedia definition here that links 3 measures of diversity: alpha, which is at the local scale; beta, which is at the bigger scale as we go from habitat to habitat across the landscape; and then gamma diversity, which incorporates both of those two kinds of diversity. Okay, so let's head back here to past. So let's head over to past, and I'll start with beta diversity for a reason which I'll get to in a moment. So let's select the lot, diversity, beta diversity, And there we go. Across here there are various indices, including Whittaker's first one and the Routledge one, which the paper which I was looking at a moment ago. Exactly what the interpretation of these values is, I'm not too sure. I'm not an expert on this aspect of diversity. Most of my work on diversity is done at the level of alpha diversity, but if you need the beta, that's where you can get it. Now, I said I would start with beta diversity for a reason that I would get to, and the reason is this. The standard file format is, as you know now, hopefully, variables go across the columns, so that's the species or taxa in this case, and samples go down. But for most of the options on the diversity menu, we need things the other way around. Fortunately, we can go edit, transpose to switch things the other way around. So diversity. Diversity just brings up a set of standard diversity indices for each of the samples. And if I go across, you see we get those for each of the 30 samples. It starts with the number of taxa, and we also get a count of individuals, and those numbers, you can see, vary quite substantially from tens up to hundreds. And in the case of sample 21 here, there was in fact only one individual, so one species in that, and meaning that some of the indices are not estimatable. Dominance and evenness are both looking at the same kind of thing, how evenly distributed the individuals are among the taxa. The cow is one of the newer ones, which is trying to estimate total diversity. So that's diversity. Next option on the menu is Quadrand richness. So Quadrand richness is calculated by converting to presence-absence data, and it's trying to make an estimate, as I understand it, of the overall diversity in the area. And interestingly, the notes in the PAS2 manual refer to estimate S that I just mentioned a few moments ago. We've done beta diversity. Taxonomic distinctiveness I cannot do for this data set because I actually need to label the rows with, I need to label the taxa, which is the rows, and I don't have that information. So that takes us to individual rarefaction, which is the kind of rarefaction that I'm more familiar with. PAST version 3 will go straight to the graph, and which is this here. It looks a bit of a spaghetti, mass of spaghetti, until we turn off the confidence intervals. And PAST version 3 will give you the lines in different colours. So what this is doing is allowing us to compare samples that have different numbers of individuals. As we increase the number of individuals in our collection, we're likely to increase the number of species, and we'll see another example of that in a moment. Now you can see by these curves that the individual samples here vary quite considerably in their richness, and this particular type of rarefaction, which they call individual rarefaction, allows us to compare samples that have different numbers of individuals. So here's the sample that has the greatest number of individuals, and what we notice is that other samples with fewer individuals may actually have more species. So by chopping through in places, we can compare the actual diversity or the diversity curves for samples with different numbers of individuals. Next on the list is sample rarefaction. Okay, now before I do this, let's go over here, because sample rarefaction is actually more commonly known as the species accumulation curve, or as you can see here, the species discovery curve. And as I'm speaking, you can read a little bit more about it here. This is a typical relationship that develops when sampling within the same type of habitat or same type of assemblage or community. The first few samples collect the common species, and then as we increase effort within that place, we're adding in more and more of the rarer species. So here, again, the graph. So this is based on all of the samples, and you can see that quite obviously down the bottom here, and it just looks at how the number of taxa we've found increases as we increase sampling effort. In the case of this particular data set, when we get to the 30 samples, the curve is still trending up quite rapidly, suggesting that there's a lot more species out there to be found if sampling effort is increased. Typically the curve will start to level off at some point, but there are theoretical statements that it may never completely flatten. So that's a sample rarefaction. I prefer the older term, the species accumulation curve, because that's exactly what it is. It's just how species accumulate as we add more samples in. Here. So this does so-called shear analysis. So we get, as you can see, 3 plots. One is log of species abundance, so that will be the top one. The middle one is H, the Shannon index of diversity, and the bottom one down here is log E, log of evenness. Now in the lower axis is number of individuals, and the samples are just added in sequential order here. So if the samples go across a gradient or across different communities, breaks in the curve or discontinuities in these curves may indicate where we're going from one assemblage or community into another. All of these samples are taken within the same type of assemblage or community, so all that's happening is the curves are varying depending on the log abundance goes up naturally, evenness goes down as we get more and more species, and the Shannon index here eventually stabilizes when we get into large numbers of species. Then we've got compare diversities, which is going to require 2 samples and diversity t-test. So I'll start with this one, which does diversity profiles for the different samples. You should read up on what is actually being done here. If I go back and just have 2 samples, then compare diversities here, calculates range of indices for the 2 samples, and then does a test comparing those indices between those samples. When you've got a large number of samples, I don't know that this is terribly meaningful. I would be looking to do it more on pooled samples for different habitats, communities or assemblages. The same here with the diversity t-test, which is an older way of doing the same kind of thing. Okay, some of that is a little bit shaky in there because it's not something I do very commonly, but it will give you a bit of an idea of the capabilities of PAST, though I do strongly recommend going and having a look at Estimate S.